Hey everybody, this is Mr. Ainsworth, and we're going to get into a lesson on compounding continuously. Now, in previous lessons in financial algebra, we talked about how to compound annually. We talked about semi-annually, compounding quarterly or monthly, then quarterly, and then daily. We even talked about doing it hourly, so it was kind of crazy. When we got really, really close to compounding continuously, compounding daily and hourly is very, very close to it. But it comes down to it, the best way to compound your money, to make the most money when you put money into an investment, is to compound it continuously. So what does that mean? What is it all about? How do you derive it? How do you derive the equation that we are going to be using to calculate the money that we would get in the future if we invest, something at a certain interest rate where it is compounded continuously. So the goals are at top here. We are going to number one, we're going to learn how to find a limit of a function numerically and graphically because it involves limits, new to the course. Number two, we want to determine Euler's Constant, E. Okay, you can Google that. You can check it out. You saw it in Algebra 2 and Pre-Calc, and believe it or not, it's involved with the compounding continuous function that we're going to be using. And to do that, we're going to be using the special limit. We're going to do it numerically and graphically. I'm going to be using Desmos, as you see on the right. Number three, we're going to derive the compound continuous function from the compounding function that we already know in the prior section, okay, that we were using how to calculate the money that we'd have in the future if we compounded either, again, quarterly, annually, daily, and so on, okay. That's, we're going to use that, believe it or not. And then afterwards, after we do all that work and that investigation, we are going to apply the compounding continuous function, which is stated right here in goal number 4. B is equal to P times E to the RT power. And I'll show you that at the end. So first of all, we got to get a few things set up. So in Desmos here on the right, okay, what we're going to do is set that up. If you haven't set up the account, what you do is you click on the Save button, and this will pop up right here. You got to put the name of your lesson in here. This is section 6 in chapter 2 in financial algebra. Put your name on it like I did. All right, and then hit the Save button. And then you can save all your work no matter what you do. And I love Desmos because it's the best online calculator. You can save your work throughout the entire course on it. You can even print it to a PDF, which you're going to be doing for me, and put it in Canvas. Okay. So on the left, you got to print your lesson. It's in Canvas. Print this first, and then set up your Desmos, and then continue with the video. And if you haven't done that, get set up before we get started. All right, let's get right into it. The first goal is to understand how to find the limit of a function numerically and graphically. Okay, so let's give it a shot. It's the first time we've done it in the course. You might have done it in you did in Pre-Calc, and I don't know if you've done it in Algebra 2, but here we go. Let's take a look at a simple rational function here. F of x equals 6 divided by x. And what we want to do is to find the limit as x approaches infinity. And so you'll see the notation on the left here. So LIM is the symbol for limit. Your symbol for approaching is the arrow. So as x approaches infinity, okay, the infinity symbol is the sideways 8, okay, and the symbol for approaching is the arrow. So as x approaches infinity, what's the limit of the function? 6 divided by x. What is that? So what we do is we analyze it in Desmos first. So I'm going to type in the function here, y equals, okay, 6 divided by x. Just type it in, and let's work with it here. So I'm going to expand Desmos so we can see a little bit better here. And you notice that it's a special hyperbola, okay? It's one of those special functions that you saw in Algebra 2, hopefully, and even Pre-Calc. And you'll notice that the function has two parts. It exists in quadrants 1 and 3 here. And what we want to do is figure out what happens to the y values when x gets large. So when you talk about what happens to a function when x goes to infinity, you're talking about what happens to the y values when x goes to the right, from, let's say, 10 to 20 to 30 to 40 to 50, all the way to infinity, so all the way to the right. So I'm going to change my scale on the x-axis here. So I'm going to condense it. See if I can do this here. So notice the x-axis now goes up to a 500 here. And notice what happens with the function here. So again, I can trace the function in Desmos here. So as you go to the right, notice that the function is getting asymptotic here, which means really, really close to the x-axis. And notice the y value. Look at the y value on the screen. When x is 230 right there, y is 0.026, so it's getting closer to 0. And if you go to the right, it gets even closer to 0. So as you go to the right, as x travels to infinity, the y values get smaller and smaller and smaller, and they approach 0. So we say the function approaches 0. Of course, it can never equal to 0 because it's asymptotic there. It never touches the x-axis, as you guys know what asymptotic means, hopefully. And right there, so we say that the limit approaches 0. Now, you can also analyze it numerically, and that's part of it here. It says do it graphically with Desmos, and then also do it with graphically with the table here. I'll do that here in a second. So let me expand this just one more time. We're going to just sketch it, okay, so that we know what's going on here. So I want you to sketch the two parts of the function on your paper. I'm going to screenshot it because I'm going digital here. All right, but you, of course, go ahead and just do a quick little sketch. So pause the video right now and just go ahead and do a quick little sketch of what you see. It doesn't have to be, exact. Just sketch it. I'm just going to clip it in here, and then just use the graph that I produce in Desmos. Here we go. And so again, pause the video if you need to, if you're working at home, because some of you guys are at home. All right, and let's take a look at this function and analyze it a little bit. What does it mean to calculate a limit of a function as x goes to infinity? Well, let's outline it a little bit here. So let me enlarge this here a little bit. So when x travels to infinity here, you're going to the right. Okay, positive values are to the right. So when x goes to infinity, it means when x gets extremely large, notice that the function goes down. Okay, so notice the arrows. We're traveling down on the function, and notice that it's approaching the x-axis here. And when you get closer and closer to the x-axis, the y values approach 0. So y is approaching 0. It never actually equals to 0. Okay, I mean you can never. This 6 divided by x will never equal 0, right? Because the numerator is a constant, 6, and the only way for a function to be equal to 0 if the numerator is equal to 0. So this function will never be equal to 0, but we say the limit, all right, is equal to 0. It approaches 0. Okay, so keep that in mind. All right, and so I'm not going to analyze what's happening to the left. I mean, the same thing's happening if we go to the left, but I'm not looking at the limit as x goes to negative infinity. I'm looking at the limit as x goes to positive infinity, all right, which means to the right. Okay, positive values are to the right. Negative values or negative infinities to the left, but I'm not analyzing that right now. All right, so let's take a look at what happens, all right, numerically. Okay, so what we want to do is when you're traveling to infinity here, all right, when x approaches infinity here, it's getting extremely large, okay? So x cannot equal 0, okay, it's not defined there. Okay, so when x is 0, it's undefined. You can't divide by 0, so 6 divided by 0, well, that's undefined, as you guys know. All right, so undefined. All right, but it can get large. So let's take a look at the values when x is 10, 100, 1,000, 10,000. And this is easy to do in Desmos. I've done this with you guys before. All right, so it should be easy for you to do again. So after that, it'd be, how about 1,000,000, right? Oops, if I can write it correctly here, sorry. Okay, and then so let's enter these values in. So you hit the gear symbol here. All right, duplicate it and then change it to a table. I've done this before with you guys in class. Just backspace and clear out the values. So notice that the second column is 6 over x because that's your y value. So let's put all the values in. Now if you put in 0, notice it says undefined because you can't divide by 0, man. Okay, you just can't do it. You never have. All right, so let's just type them in. So 10, 100, 1,000, 10,000, 100,000, million. All right, and notice what's happening to the values here. Let's record them on our paper here. So on this right here, y starts off when x is 10. 6 divided by 10 is 6/10, so that first value makes sense. All right, and then it's 600ths, okay, and then 6,000ths. It's getting smaller, so as x is increasing, y is decreasing, just like in the graph, okay? And then 6 times 10 to the negative 4 is 0.0006. And then 6 times 10 to the negative 5, that's 0.00006. All right, and then 6 times 10 to the negative 6, you got to shift it 6 places back to the left with 5 zeros as placeholders. So it goes 0.00006. All right, and so as x is increasing here, as x increases, all right, y decreases, all right, and we say that y is approaching 0. All right, well, just look at the values, right? That's very, very close to 0, guys. So when x gets really, really large, the limit is 0. So you can see it graphically on the graph, and you can also see it in the table. All right, we say that y, look at this, y is approaching, never equal to, but approaching 0. These decimals are very, very small, guys. So there we go. That's the first one. Now we're also going to take a look at another function here, so another rational function, but this time f of x equals 6x minus 5 divided by 2x plus 1. We want to find the same limit as x approaches infinity. And the way you write that is x approaches infinity. So notice that it's right over here. All right, and so what is the limit? Okay, well, if you don't remember your stuff from Algebra 2 and Pre-Calc, well, let's figure it out. All right, so let's go to Desmos. Let's deselect the colors, which means just turn off the graph. All right, do not delete them. That would be a bad move because you're saving your work here. In fact, hit the save button. All right, and let's put the next function in. So here we go. So let's type in y equals the quantity 6x, all right, minus 5. And notice that I put parentheses around the numerator because I have to hit the division button and it makes it a fraction, right? To do that requires the parentheses, so remember that. If you don't type them in, you'll see it's not going to turn out right. So just try it without parentheses, you'll see what I'm talking about. All right, so there's your function. So let's take a look at it. Now, this function obviously is a different rational function, and notice it's different. And what we want to do is analyze it graphically and see what it approaches when you go to the right, when x approaches infinity. When x goes from 20 to 40 to 60 to 80 to 100, when it gets really, really large, what really happens. So you put your cursor on the graph and you go to the right and look at the y values. What's happening to those y values? Okay, and so what's going on? They're getting bigger a little bit, but they're not getting bigger by much, right? What are they approaching? What do you think? So let me zoom in here, right here. Watch this. Let's go to 300. So I just changed the scale there. So when we go to, let's say, with 300, look at this. The y values is 2.987. Go to 400. Let's go further out. Okay, so let's go to 1,000. Look at this. So when you go past 1,000, like 1,200 right there, y is 2.997. It's getting really close to 3. It's flattening out at 3. And if you want to test that conjecture, okay, all you do is type in y equals 3. So let's do that. So when you test horizontal asymptotes, you just type the horizontal asymptote in, y equals 3. And look at that. Look at let's change the color here. Let's change this, hit the gear symbol. Oops, sorry. Hit the gear symbol, and then you hit the color here, I think. Let me see. Yep. And let's change it to red just for funsies here and make it a dotted line. All right, because it's an asymptote. So here we go. All right, so there's the horizontal line in red is y equals 3. And notice that your graph approaches it, right? It gets closer to it. It never crosses it, never touches it, never reaches y equals 3, but it gets pretty damn close. All right, and so we say the limit is 3, guys. All right, so let's take a look at the table of values here too. Well, actually, let's just record that. Okay, so go ahead and do a little sketch. Okay, so what you do is you sketch the asymptote first. So go up 3 units. And then if you're doing this on paper, just do what I'm doing. So y equals 3 here. And then draw your little sketch here. So it looks like this. No. Okay, boom. Okay, there you go. And the other part's up here. No. Okay, you got to put in the sound effects. All right, so draw your little sketch and then detail it. So when you go to infinity, when x approaches infinity here, all right, look at the function. It goes up, 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 and y is approaching 3. Now, does that happen with the table of values when we create it? I don't know. Let's find out. All right, so let's create a table. So hit the gear symbol. All right, and then duplicate the function. All right, and then hit the table button, and notice the table appears. And like we always do in class, because I've done this for you before, you clear out the values and start putting them in. All right, evaluate the function for you, which is kind of nice. I mean, Desmos is the coolest graphing tool there is. I mean, GeoGebra is really cool too. So if you're a GeoGebra fan, all right, don't knock me down here. They're both great programs. Okay. Okay. So now let's evaluate the table, or evaluate the function using the table. So we want to figure out what happens when when x gets large. Okay, so let's do that. 10, 100, 1,000, 10,000, 100,000, 1 million. All right, 10 million. Okay, this is when x goes to infinity. That's what I'm talking about here. So as x travels to infinity, when it gets very, very big, what's happening to the y values? And all you have to do is just type them in, guys. So 10, 100, 1,000, 10,000, 100,000, a million, 10 million. All right, and look at the values. Look at all these y values here. All right, and they start at 2.6 and then go 2.96, 2.996, 2.9996, 2.99996, 2.9. Okay, these values are obviously getting closer to 3. So let's record it. Okay, so the first one is about 2.6, 2.96, 2.996. The next one, 2.9996. Next one, 2.99996. And then, the pattern continues, right? So you get the point here. So it's getting really, really close to 3. So here, y is approaching 3. Here, x is approaching infinity because it's getting extremely large. Okay? And so the limit approaches 3. The function never is equal to 3, okay? But the limit, we say, is 3. There's a big difference between equals and limit. Okay, so that's an idea of how you get a limit of the function using tables and graphs, okay? Using Desmos. Make sure you hit the save button, by the way. All right, let's get into our second goal. Let's take a look at Eulers, the famous Eulers constant here, which is denoted by E, okay? Eulers constant, E. He came up with this. He derived this many, many years ago. You can Google that, by the way. All right, and so what we're going to do is we're going to analyze the limit of this function here. All right, so we're going to go into the next available line in Desmos and type it in. So y is equal to, all right, the quantity of 1 plus 1 divided by n. Just type in your function. Actually, let's do 1 divided by x. I'm sorry. Look at the function here. F of x is equal to 1 plus 1 over x to the x power. Okay, make sure you get out of the denominator here by clicking the right arrow key. All right, and then close out the parentheses and then use that a to the power b button, that exponent button, all right, and raise it to the x power. Now deselect the previous functions, so turn off the colors. I don't mean to delete them, okay, so you don't want to delete your work. All right, just deselect the colors, so you're looking at one function only. And let's look at this. Okay, so here's the function right here. Notice it's a two-part function again. And notice it's flattening out again. So what happens when x goes to infinity? What is the y value approaching? Okay, so let's change the scale a little bit. So you can obviously flattens out, it approaches a value that's in between 3 and 4. It looks like it's over 3 and under 4. But what is it really approaching? When you get really far out there, when x goes to infinity, like to 10,000 to a million, what is the y value approaching? Is it 2.7 like on the screen? Okay, or is it a little bit bigger? Okay, it definitely is under. It's greater than. Oh, what happened here? Why did I say between 3 and 4? Okay, look at here's 2 and then here's 3. I'm sorry, it's between 2 and 3. I'm sorry. So it's greater than 2, and then it's under this. 3, level 3 here, so it's under 3, and it's obviously bigger than 2. It's bigger than 2.5, by the way. So what is it? What is it? Is it 2.7 something? What is that number? Okay, so let's get a table again. So here we go. So we're going to duplicate it, and then we're going to get a table in the second row. All right, and then we're going to enter in some really big numbers here because we want to see what happens to the y values when x gets large. All right, so type in 10, 100, 1,000, 10,000, 100,000, a million, which has 6 zeros, 10 million. All right, and look at this. Look at the values here. So I'm gonna just screenshot this here real quick and bring in these values. Actually, let me do this one more time. Okay, here we go. So I can get the values here. I love technology because, oops, I missed it. Sorry. Let me do that one more time. Pardon me. Excuse me here. Let me do a screenshot one more time, and then we'll analyze the numbers here. Okay, there we go. All right, so let's go back to our lesson here, and let's record a few things. So you guys type in the numbers, okay, from Desmos. I'm gonna just paste it in because I have technology here, and you guys go ahead and pause the video right here, and then go ahead and record those values. Okay, make sure you pause the video and record them. All right, so this is what we get when we use Desmos on the values here. So as x is approaching infinity here, as x is getting really, really big, look at these y values: 2.5, 2.7, 2.716, 2.718, 2.71826, So it's not changing after 2.78. So after the fourth digit, it's not changing. All right, it is in the beginning, but not at the end. And so y is approaching, not equal to 2.718 here. All right, and guess what? That is your famous Euler constant right there. All right, and you can Google that. Type in the word Euler's constant, and you'll see that approximation right there at 2.718. There's your approximation. Now, so if you're going to sketch this, okay, so let's do that. All right, so go ahead and sketch this is y equals e, all right, or you can say y is equal to 2.718, okay, that horizontal line that I was talking about. By the way, let's do that. Let's type in y equals e so you guys can see it. And what's beautiful is that you just type in y equals e. You go to the keyboard here and you type in e, and then voila, Euler's constant comes out. Look at that, 2.718. Even Desmos knows what's going on. Okay, and so, and it's a two-part function here. So it's asymptotic to the line y equals e in red, and then it's also asymptotic to the y-axis as well. So when you draw this, just draw a really good sketch. Okay, so here we go. So, oh, wait a minute, sorry. Backwards. Okay, like this. Okay, so give a good sketch. All right, so as we were talking about here, as x approaches infinity, the y values are getting bigger and bigger and bigger. And guess what? Y is approaching that famous number e, which happens to be 2.718 approximately. All right, so e is approximately equal to 2.718. That's Euler's constant. You pronounce it Euler, okay? Not Euler, but Euler. Something's wrong with my pen right now, so I apologize. I'm trying to fix it as we speak here. Okay, now let's get on to the derivation. So here we go. Derivation, goal number 3. All right, how do we take what we know about the compound interest formula here, which you already know, and how do you derive the compound interest function, which is b equals p times e to the RT power. Whew. Okay, here we go. So our goal is to show that b is equal to, all right, p times e to the RT power. So I've got to get from this right here all the way down and step it out and somehow show you and prove to you that if we take a limit here as of this function that I'm going to start with here, that we get the compound interest function or continuous function that involves e, the Euler's constant. So here we go. I'm going to throw a little bit of math at you. All right, so we're going to start off with this. This is what we know. So b is equal to p, principal, times 1 plus r divided by n to the nt power. And this is what we know, okay? So, and again, my goal is down at the bottom of the screen. I got to get down there somehow. So what I'm going to do is going to rewrite something. And I'm going to rewrite r divided by n, the periodic interest rate. So I'm just going to rewrite it. And I'm going to do a little bit of side math here. So I'm going to rewrite r divided by n. So r divided by n is actually can be rewritten as 1 divided by n divided by r. Okay? Now, if you don't believe me, then just go back to grade school for a second. When you divide a number by a fraction, all right, you were taught to multiply by the reciprocal. So from here to here, I can multiply, all right, by what's called the reciprocal. Okay, going back to grade school just for a minute. If you guys don't know why, I can rewrite it like that. And this is actually equal to 1 times the reciprocal, which is r divided by n. There's your reciprocal, which is obviously r divided by n. All right, so these two expressions are equal. So keep that in mind. All right, so I'm going to rewrite it here. So I'm going to start off with our function. B is equal to p times 1 plus 1 divided by n divided by r raised to the, excuse me. Let me use different parentheses here. Let me go back here. I'm going to use 2 sets of parentheses. You'll see why in a minute. So just work with me here. So we got p times a quantity, 1 plus, all right, 1 divided by n divided by r. Okay. And now I'm going to rewrite the power here, the power nt. Okay. Now I'm going to go, before I rewrite it and finish this here, you need to understand something from Algebra 1. Okay, so this is from Algebra 1. Okay, so just let me show you something here. Back in Algebra 1, we had something like this right here. 2, let's say, to the 3rd power. And then you squared it. And you have a power to a power. Now, when you have a power to a power, you multiply exponents. So this is actually equal to 2 times, or 2 to the power of 3 times 2, or 2 to the 6th power. Okay, and you know that has to be true because 2 to the 3rd squared means 2 to the 3rd times 2 to the 3rd, which is obviously 3 plus 3 is 6 right here. When you multiply like bases, you add exponents. And so this is 2 to the 6th power, and notice they're the same. So when you use a power to a power here, you multiply exponents. So I'm going to do another mathematical trick here. So I'm going to raise this to the power of n, not nt, but of n divided by r. All right, and then I'm going to raise it to another power, r times t. Now, why is this all equal to the function above? Okay, so let me prove this to you. So take a look at your exponents here. I'm talking about n divided by r to the rt power. And then come back down here. I'm going to show you that they're actually equal to. So power to power, you multiply exponents. So theoretically, I have to multiply these exponents, and it better be equal to what we started with here, which is in yellow. It better be equal to nt. So the power of n to the r raised to another power, r to the t power, better be equal to the nt power. So let me prove that to you. So we take n divided by r times rt. All right. When you multiply fractions, you simplify a little bit. R divided by r is 1, and that gives you nt, which happens to be right up here. Okay. So just rewriting this expression, all right, allows me to do something really, really nice. Okay, so I know what I've done right there is just a little bit of magic, mathematical magic. All right, I just rewrite the function in a special way because this right here in the middle, okay, is important. Okay, this portion here in the middle, I'm talking about this portion. So what I'm going to do is I'm going to let n divided by r is equal to x. All right, and I'm going to just do a variable substitution. Okay? Substitute. Okay, here we go. So I'm going to substitute in x where I see n divided by r. There's 2 places. So now I have b is equal to p times, okay, now I've got this function here, 1 plus 1 divided by x. Now n divided by r became x because they're equal. I just substitute. Raised to the x power, and that's all raised to the rt power. Okay, now this is where I want to take a limit, okay, of the function. So what I'm going to do is I say b is equal to the limit as x approaches infinity of p times 1 plus 1 over x, all right, to the x power raised to the rt power. What is this? Well, later on, this can be proven later on, not now because we don't have enough mathematics, but you're allowed to distribute the limit inside a function like this. So really this is equal to p times the limit as x approaches infinity of 1 plus 1 over x raised to the x power, all right, raised to the RT power. So let's do this. Here we go. Now we take the limit. Now we just talked about a very special thing above here. So let's go back to our lesson. We talked about the limit of 1 plus 1 over x to the x power. I should have changed. This should be x in here, and this should be x here. And we talked about how it's equal to or approaches e. Okay, it's actually equal to e. That was the limit, where e is 2.718. So because we know this, I get to apply it here. So as soon as you take the limit of our function, all right, this right here approaches e. So what I get is b is equal to p times, again, there's e here, it approaches e, raised to the RT power. RT power, and if you just want to rewrite that without the parentheses and make it look nicer, p times e raised to the RT power. And that, my friends, was our goal. So when you invest money, when you're given a principal and you're compounding continuously here, you're going to be using this function where p is principal, r is your interest rate, and t is time, if you're compounding continuously. So this is if compounded continuously. Okay, it has to give you that kind of vocabulary. It has to say continuously, not quarterly, monthly, daily, and all that. It has to be compounding continuously. All right, now let's apply it. Here we go. So in this case, all right, B is a future balance. P, principal, that's the initial deposit. Okay, R is your annual interest rate. Okay, remember to express that as a decimal, and this is the time in years. So most of this stuff is already known. Okay, you already know all of this right here. The only thing is we have to apply it. All right, so let's apply it, speaking of that. Okay, so here we go. Okay, our first one here, if you deposit $20,000, there's your principal. So P is 28,000, or excuse me, 20,000. Come on, Ainsworth. So $20,000. Okay. R is 1.85%. All right, and that's equal to 0.0185. And if it's compounded continuously, look at that, guys. Okay, look at that. What would you earn after? Look at this, 3 years. So T is 3 years. All right, so here we go. It's very simple, actually. So B is equal to the initial deposit, principal, all right, times E now, raised to the 0.0185 times the time in years 3. And then you just simply enter that in Desmos and you get a value. I mean, it's that simple, believe it or not. Let's go to the next line in Desmos, type it in. Here we go. So 20,000. Okay, make sure you get the correct number of zeros there, 20,000. And then you go to the ABC button, which is your keyboard. You type in E, or use your own keyboard, okay? To the power of, so hit the A to the B button, okay, your exponent button, and raise it to, and put this in parentheses now, 0.0185 times 3. All right, and notice it gives you a value bigger than 20,000 because the money is growing, all right, and compounded continuously. So which means the interest there, the bank's putting interest in actually every second of the day. It's actually even better than that. It's every fraction of a second during the day. So this is $21,141, all right, and 38 cents. Okay, that's all there is to it, believe it or not. It's actually quite simple. It's actually easier than the previous formula. Now, how does that compare to compounding monthly, and how does it compare to quarterly and annually? Okay, so let's do the same calculation, same principle, same interest rate, but let's compare it to what it's like compounding monthly. Now remember, the compound interest formula that we used previously looks like this, okay? And so we know everything that we need to know. So, but in this case, when you compound monthly, all right, so again, we're going to compound monthly here. That tells you what n should be. So we're going to do monthly, and then quarterly, and then semi-annually, and we're going to compare the values. Now, if you do it monthly, right here, n is 12. When you do it quarterly, n is 4. When you do it semi-annually, m is 2, right? Because there's 2 semi-annual periods, because these are 6-month periods. All right, so here we go. So the future balance would be 20,000. All right, times 1 plus r, which is whoa. Oh, you know what? There's a typo in my lesson here. So change this, guys. These should all be 1.85. So 1.85%. 1.85%. That's a typo. 1.85%. They should all be the same. Okay? Apologize for that. Your printout should have that fixed. So that shouldn't be a problem for you. Okay, so let's go 0.0185. Okay, we got to divide it by n, which is 12, because we're doing this monthly. So that gives you your monthly periodic rate raised to the nt power. So here n is 3 now, or I mean, excuse me, n is 12, but t is 3. T is 3 years. So it's 3 times 12, or you can put 36 there. That would be really nice. Okay, and let's figure that out. Now, it's not going to be good as compounding continuously. It should be less than the previous answer. So let's type in 20,000. All right, times the quantity 1 plus, all right, 0.0185. All right, divided by 12 because it's monthly now. Get out of the denominator and close off the parentheses before you raise it to the 36th power. All right, 3 times 12 is 36. And notice that we have a little less money because this is not as good as compounding continuously. All right, so B in this case is $21,140.48. Okay, so it's not as good as compounding continuously. This is the best way to make money. Okay, best way to make money. Write that down. All right. Now, what is it quarterly? Quarterly and semi-annually should be less than monthly because the more you compound it, the better it gets. So here, okay, so let's try quarterly. So quarterly n is 4. So B is equal to 20,000 times 1 plus 0.0185. Again, we're using the same interest rate in all these problems so we can compare it. Divided by 4 now, raised to, let me see, how many quarters in 3 years? Let me see, T is 3 years, there's 4 quarters per year, so 3 times 4, that should be 12th power. So raise that to the 12th power now. All right, well that's easy. Okay, so let's enter in 20,000 again. All right, times 1 plus 0.0185 divided by 4, because there's 4 quarters per year. Raise that to the 12th power, because there's 12 quarters in 3 years. So there's 12 compounding periods. And notice it's less money because you're compounding less times. The less times you compound, the less money you have overall when you're all done. All right, and that's why everybody says compound your money in a continuous fashion to make the most. All right, the more times you compound, the faster your money grows and the more money you will have at the very end. And the last one here, what we want to do is take 20,000, all right, times 1 plus 0.0185 and divide that by 2 to get a semi-annual rate because there's 2 6-month periods in a year. And again, T is 3 years in this case, right? And there's 2 6-month periods in every year. For 3 years, that's 6 periods, or you can write down 2 times 3, or just simply do that in your head and you get 6, right? 6 periods right there, 6 6-month periods. And so what is that equal to? Well, easy to figure out. Just type it in. And that's why I suggest you guys use Desmos, because once you do all this work, you get to reuse it, by the way. When it comes on future problems, quizzes, tests, projects, oh my God, all this is here. All you have to do is modify the numbers. And so be smart, use Desmos, and then save your work. A little tip there from the pro. All right, and then divide that by 2, because this is a semi-annual calculation. Take that to the 6th power. Oops, I didn't type in a to the b, and you got to raise it to the power of 6, right? And notice it's less money, right? Because you're not compounding as much. Okay, so all this is money, so put dollar signs on everything. All right, and there we go. So notice that the less you compound it, the less you have. Conversely, the more you compound it, the more money you have. And so the best way to do it is at the top, guys. Compounding continuously is the best way to compound your money. You will make the most money possible over a period of time. Okay? And that's it. That's the whole entire lesson, the whole shebang. All right? This is Mr. Ainsworth here. As with all the videos that I produce, if I go too fast, well, guess what? There's a rewind button, right? And then go ahead and rewind. Go ahead and take a look at it again, because I probably don't go at your pace. I usually don't. So just use your video effectively here. Okay, my name is Mr. Ainsworth. I work at Great Oak High School in financial algebra here. All right, and there you go. I will see you in class, you guys. Take care. Hope this helped you out. Bye-bye.